Math analysis. Here we go for lesson 4. Let's do some more multiplying radical expressions, especially now that we know how to add and subtract radical expressions. All right, back to the basics, the simplifying, the thing it all hinges on, right? So we look at our radical 48 and we think, oh, well, that's not a perfect square. But is it divisible by a perfect square? And sure enough, 48 is divisible by 2 perfect squares. If you look at my graphing calculator up here, I've still got it right there. So there we go. What's the biggest perfect square 48 is evenly divisible by? It's 16. So I divide 48 into radical 16, it's perfect square. And 48 divided by 16 is 3, it's leftover. And I take the square root of the perfect square. Square root of 16 is 4. Bring the leftover with, and 4 radical 3 is my final answer. You always have to simplify radicals if they are evenly divisible. If that radicand is evenly divisible by a perfect square, that perfect square factor can never stay under the radical. So you always bring it back out. Same thing goes with variables. Any even exponent on a variable is itself a perfect square, and any exponent over 1 on a variable means there is a perfect square factor in there that can come out. So we divide into the perfect square radical and the leftover radical. Let's start with the number. 4 is the biggest perfect square that divides evenly into 12. 12 divided by 4 is 3 for the leftover. X to the 5th, what you do with the exponents, subtract 1. So 5 minus 1 is 4. That means x to the 4 is the biggest perfect square that can come out. That 1 is the leftover. That x to the 1st is the leftover. Okay? Unless it's even, and then the whole thing is a perfect square. So now take the square root of the perfect squares. The square root of 4 is 2. The square root of x squared is the square root of x to the 4th is x squared. That's your coefficient. Bring your whole leftover down. Your final answer is 2x squared radical 3x. Say that. 2x squared radical 3x. Nice. Heard you guys from afar. You did really well. Very synchronous at that time, too. Okay, so here's the deal. As we know from lesson 2, when we multiply radicals together, multiply the outside numbers together, the coefficients, multiply the inside the radical numbers together, make sure there's not anything else that could come out. Okay. So now that we've got bigger radicands, bigger situations that we can multiply, we can do distributing, we can do foiling now with radicals, because if we get a couple of radicals, we know that we could add and subtract them. So here we go. This is the regular multiplying because we've just got an outside number times an outside number. That inside radical 2, that's going to remain. 6 times negative 3, that's negative 18 radical 2. Radical 2 is as simplified as it gets. Boom, you're done. Sometimes that happens, which is great. Unfortunately, more often than not, this is the kind of thing that happens. So outside numbers multiply together. Negative 5 times 2 is negative. Got 2 equal signs? Weird. Negative 10, radical 12, 5, x to the 5th, and radical 8x to the 3rd. Okay, so multiply the numbers together first. 12 times 8, in case you don't know. It's 96. Oh, it's 96. And x to the 5th times x to the 3rd, just add your exponents because they're the same variable. So when they're the same variable and you're multiplying the exponents together, or multiplying those two bases together, you can just add those exponents. It's exponents rules back from Algebra 1. We'll talk about them again, actually, this year. But now what I have to do is see, is 96 evenly divisible by any perfect squares? So I think 96 has a couple. Let's find them. 96, start with the first perfect square we can divide these by. It's 4. Yeah, there's another perfect square in there. That's a pretty big leftover, and that leftover is divisible by a perfect square. So if you do that and you get a leftover that's evenly divisible by a perfect square, you have to keep going, keep trying. So I know that 96 isn't evenly divisible by 9 because its digits do not add up to something evenly divisible by 9. 9 plus 6 is 15, not divisible by 9, so 96 isn't. but 96 divisible, oops. There we go. Try it again. Divided by 16. And look at that leftover. Not evenly divisible by any more perfect squares. So now I know what the biggest perfect square that divides evenly into 96 is. So I bring down my coefficient, negative 10. Bring down a perfect square and a leftover radical. 96 divides into 16 and a leftover of 6. Now I think about x to the 8th. Is that an even exponent? Yes. So the whole thing is a perfect square. There is no leftover for the variable. Take the square root of the perfect square stuff. Square root of 16 is 4. Square root of x to the 8th is x to the 4th. And now multiply it by the coefficient that was already there. Negative 10 times 4 is negative 40. There we go. X to the 4th, and then bring down your leftover, radical 6. So your final answer, a little bit of simplifying happened there. Your final answer is negative 40, x to the 4th, radical 6. That's your final answer. That was the kind of multiplying we did in lesson 2, but now we can distribute. And we know that that is a type of multiplying. When you multiply these, outside numbers multiply together, inside numbers multiply together. If you don't have either, then you don't have to worry about it. Like right here, 6 times negative 5, well, that is just negative 30, so there it is. Now it's 6 times 3 because they're both outside numbers. And the inside remains because there was not another radical to multiply it by. There is a situation, this is a situation where you've got a rational number here and an irrational number here. And since they are not the same number set, they cannot add or subtract any further. That's it. You're done. Everything is simplified. Those can't add any further. Let's try B. Now this time, it's 2 radical 3 that gets distributed. And so this 3 right here, that's an outside number, and 2 is an outside number. So you multiply those together to get 6, and radical 3 just comes along because it doesn't have anything else that it can change numbers with. Now we do it again. This time, the only number in front of this radical is a 1, so 2 times 1 is 2. But now the numbers underneath can multiply together because they're both under radicals. So 3 times 12 is 36. Now what you do is look to see if you can simplify these radicals any further. Obviously, radical 3, we're done there. But 36 is a perfect square, so you take its square root and multiply these two numbers together. Now, when I write my final answers, I always write any rational numbers first. So any whole numbers or rational numbers that come out, I'll write them first. 2 times 6 is 12 in the front. And then this was a positive 6, radical 3 in the back. That's my final answer. Again, 2 different number sets, can't combine. Okay, here we go on another one, distributing. Multiply the outside numbers together, 30 radical 2. Multiply the outside numbers together, negative 18. And the radical 2 times radical 2 gives me a radical 4. Yep. What is the square root of 4? It's 2. So these multiply together. Again, I'm going to put that in front because I like to put my rational numbers first. So negative 36 plus 30 radical 2. And yet again, cannot go any further. Different number sets, cannot add or subtract further. Okay. Ooh, lots going here. Okay. So negative 2 radical 6 times radical 3. Okay, so negative 2 times 1 is negative 2. Radical 6 times radical 3 is radical 18. I'll simplify that in a minute. Let me keep distributing first. Negative 2 times positive 2 is a negative 4. Radical 6 times radical 6 is a radical 36. I'll simplify it in a minute. Let me keep distributing. Negative 2 times negative 1 is a positive 2. Radical 6 times radical 12 is radical 72. And now all of these radicals can get simplified. Okay, so let's start over here. Negative 2 Perfect square is 9. Leftover is 2. What's the square root of 9? 3, right? So negative 2 times 3 is negative 6 radical 2 in the front. Okay. So that's this one. We'll add them all in a sec. Let's start here, middle. Negative 4 times, oh, what's the square root of 36? 6. So I get this as negative 24 as a whole number answer. I'll rearrange for my final answer so I can put that number in front. The biggest perfect square that divides into 72. So let's see, 72 divided by 4 does work, but that's definitely not the biggest perfect square. So let me try 72 divided by 9, which I do know works because 7 plus 2 is 9, so it's evenly divisible by 9. But still, that leftover still can simplify. So let me try, what's 4 times 9? 36. I heard you say it, Ella. There we are. There we are. So now I've got that smallest leftover. So this divides into 36 and 2. What's the square root of 36? So I can multiply those together. I get plus 12 radical 2. Now, any like radicands can combine. So these both have a radical 2. So add their numbers in front. Negative 6 plus 12 is positive 6 radical 2. I'm putting my answer right up here by the equal sign. And I said I wanted my number in the front. So negative 24 going in the front, that's my rational number, was a positive 6 radical 2 in the back. There's my final answer. Can't combine any further. Notice the only two I could combine were the ones that had the same number under the radical. Looking good. Looking good. Take a break, take a breather if you need to. Because now we're going to FOIL. My favorite four-letter F word. First, outer, inner, last. Here we go. All right. So you'll note that I have color-coded how each works, right? So our binomials. All right. This is how, when we have two binomials multiplied together, there's 4 multiplications that are occurring. The first 2 numbers in each, the outside numbers in each, the inside numbers, and the last numbers in each. And so each of the different multiplications occur. If I have any like terms, I add them up to get a final answer. You can do the same thing with radicals, and that's what we're about to do. Okay, so this is binomial multiplication. Okay, so this is FOIL. So let's start to FOIL. Okay, yeah, we're going to have a cool thing happen on number 3. So I'll start here. First, 2 times 3 is 6. Outer, 2 times radical 8 is plus 2 radical 8. Inner, 3 times radical 8 is plus 3 radical 8. There's some like terms. Last, if you have the same radicand, you can just drop the radical. That'll be the leftover. And let me show you why I know that. Radical 8 times radical 8 is plus radical 64. Well, what's the square root of 64? It's 8. So I could just drop the radical there. So now what I do for the end is I combine any like terms. And since this was a perfect square and I took its square root, these two numbers are now rational. They can add up. So 8 plus 6 is 14 for the front. Then I get 2 radical 8s plus 3 radical 8s. Well, that's 5 radical 8s. And you think you're done, except was radical 8 simplified in the first place? Nah. So that is actually radical 4 radical 2. And what's the square root of 4? 2. So 2 times 5 is 10 radical 2. That is what my final simplest form of that radical is. Throw that 14 rational number in the front and you are finally done. You've got to make sure there are no perfect square factors left under in your radical. Okay, so no perfect squares under the radical. If there's even a factor, it's got to come out. That's what happened here. Okay. Let you breathe on that for a sec. Oh, we got some fun times coming on number 2. Okay, so first, 4 times 5 is 20. Outer, 4 times negative radical 12, so that's negative 4 radical 12. Okay. Inner, okay, so negative radical 3 times 5, that's negative 5 radical 3. And last, that's negative radical 3 times negative radical 12. That's positive radical 3 times 12 is 36. Ooh, okay, well, that's nice. That's a perfect square. What's the square root of 36? Thank you, Sav. That's 6. Now combine those, so at least we know those are two radical numbers. They're both positive. We add up 26 there. We got a mess going here, though, because as of right now, that's a 12. That's a 3. They cannot add up. But 12 has a perfect square factor, so let's bring that over here. Negative 4, perfect square, left over. 12 is evenly divisible by 4. 12 divided by 4 is 3. What's the square root of 4? 2. So negative 4 times 2 is negative 8 radical 3. Look, right? Now I've got like terms. That's like. So negative 5 plus negative 8, that's 26 minus 13 radical 3s. There you go. Can you see why I didn't do this in lesson 2? We needed to make sure we knew how to add and subtract. Okay, last one where something cool is going to happen. Something cool happens here. Radical 13 times radical 13. I get radical 169. As we know, I could have just dropped the radical sign and wrote a 13 there because this is a perfect square. But let me keep going because something cool is going to happen. Radical 3 times positive 4. That's a positive 4 radical. I say radical 3. I mean radical 13. Good Lord. Correct me. Man, how come I couldn't hear that, but I can hear all your answers? Inner. Negative 4 times radical 13. Negative 4 radical 13. Wait a minute. Let me finish. Negative 4 times positive 4 is a negative 16. What's happening in the middle? Those are like terms, but 4 minus 4 is 0. So am I going to have a radical at all? Because we said this is a perfect square. The square root of 169 is 13. These have canceled out to 0. This is negative 16 left. 13 minus 16 is negative 3. My answer is negative 3. There's no radical left. What happened to the radicals? They canceled out. This is a special thing called conjugates. When you've got the same radical and the same number in two binomials that are multiplying together, but the signs between these are opposite, this is called conjugates. Okay? So that's what we're going to learn about here. Conjugates multiply together to have the radicals cancel out. Okay? Conjugates multiplying together are the only types of radical multiplication that you can actually do on your graphing calculator. So let me show you. Okay? You've learned how to FOIL the long way, but when you have a conjugate situation, you do not have to. Okay? So notice I'm writing, oops, let me go back. Got to get out before I end my parenthesis. There we go. I'm writing the first binomial, and then I'm going to write the second binomial. Come out before you hit the end parenthesis. So that's exactly the problem I have here. It's exactly the problem I have here. And I press enter, and I get an integer answer. Conjugates are the only radical multiplication that you can enter into your graphing calculator and get the answer correct. okay? Because otherwise, you're going to have radical leftovers, and the graphing calculator is going to try to rationalize them, but it can't. And so you end up with some weird, crazy answer. But this is going to give you an integer. So because it gives you an integer answer, you can do it in your graphing calculator. Let me just prove, by the way, that that's what I get when I FOIL. 4 minus 2 radical 3 plus 2 radical 3 minus 3. These cancel out. What's 4 minus 3? 1. It's pretty cool. What I want you to be able to see when we do these are I want you to be able to create a conjugate if you're given a binomial with a radical in it. So we just need to create a conjugate here. Just change the sign in between them. So 2 plus radical 5 is its conjugate. Just change the sign between them. 17 plus radical 5 is its conjugate. Just change the sign between them. 2 plus radical 11, that's its conjugate. Just change the sign between them. Negative 5 minus 6. Negative radical 5 minus 6, excuse me. Only change the sign between them to create a conjugate situation. Okay? Just change the sign between them. So 12 minus radical 30. 16 minus radical 10. 28 plus radical 13. Radical 35 plus 34. These are the matching conjugates to each of these binomials I've given you. If you multiplied those together, you get an integer answer. That's going to be key when we start rationalizing our radicals. Okay, that's going to end up being key for us. Now, some questions on your homework are like this, where part of it I want you to state yes or no as to whether or not these are conjugates. So the answer here, yes, these are conjugates. Why? Because they're the same numbers in the binomials, but different signs between them. And when that's the case, you can just go straight to your graphing calculator and enter them. Okay? So this is fine by me. Coming to the graphing calculator and using the tools at your disposal to get your answers. That is fine by me. Okay? So notice I plugged it right in. I press enter. I get my answer. Conjugates will come out to be integers. Is this a conjugate? No. If you write out a binomial squared, it's the same binomial times itself. Okay, so let me just show you real quick. I'll scooch this over so you can see that I wrote out the same binomial times itself. But I just want to show you. If I tried to do this in my graphing calculator, this is not conjugates. This will not give me an integer because it is not the same numbers with different signs between them. It's got to be the same numbers with different signs between them. Okay, this is the same numbers with the same sign, so that's not going to give me an integer answer. In fact, you will have to FOIL these. And actually, what you'll discover, you will get radical 3 times radical 3, of course, is radical 9, and the square root of 9 is 3. So you will still get one of those to work out where you've got a perfect square at the end. And so you can combine your integers and you can combine these like terms, right? So you get 12 radical 3, but that is your final answer. And notice that is so not what the graphing calculator gave me, because the graphing calculator will just rationalize your radical instead of recognize that these are not in the same number set. This is rational, this is irrational. They can't actually add and subtract. The graphing calculator wants to rationalize so it can try to add them together. Okay. So again, this is what we're looking for on our homework. Be able to look at them and say, oh, conjugates or not conjugates? Not conjugates. No, not conjugates. So when you FOIL this time, 3 times 3 is 9. 3 times radical 5 plus 3 radical 5. 3 times radical 5, that happens again. And at the end, radical 5 times radical 5 is radical 25. And what is the square root of 25? Why, thank you, it's 5. Now combine like terms. So these guys add up to 6 radical 5. And right here, that would be 14 plus 6 radical 5. I always put that rational number in front just so you get used to how I write my answers. Can you add that 14 at the back? Sure. Okay, but I write my answers this way. So you'll get used to seeing that. Then 12 are those conjugates. Same sign here, different sign here, yes. So I get to come to my graphing calculator and just put them right in. Oh, shoot, I can't see. Hold on. There it is. -8 plus radical 7. Out first, then parenthesis, now front parenthesis, -8 minus radical, radical 7. Out first, then end parenthesis. There we go. And enter. 57 is my answer. Well, that makes sense because -8 times -8 is 64. And this would give me -7. So 64 minus 7 is 57. That makes perfect sense. Alrighty, guys. That was on the longer side. There was a lot going on there. We reviewed, and then we got into distributing, and then we double distributed, which we like to call FOIL because it's awesome. All right, so make sure you've paused or gone back or rewatched if you had any struggles. Only use the graphing calculator, multiply conjugates together. I haven't shown you the graphing calculator for anything else because you cannot use it for anything else. It's not because I don't want you using it, okay? I am more than happy to show you those things. I like you using your tools at your disposal, but this is a case where you can't. The only time you can use your graphing calculator is if you're multiplying conjugates together, okay? Alrighty, guys, good luck. Please let me know if you have any questions on these. And I shall be seeing you for lesson 5, which is when we're going to rationalize. We'll split that up so that we're not doing all the rationalizing at once. We'll kind of ease in. Okay? Bye, guys.